Okay. In my opinion, we're not learning anything new. We're taking everything that we've learned and putting it together with some pre-calculus concepts. Okay? Essentially, the goal is for me to give you an equation and you use your calculus magic to graph it without touching your calculator. How will we need to do that? Okay. Here are some steps I'm going to give you. These are the things I'm going to ask you to consider. Chris, is this making you nervous? No. Okay. Each time I give you a curve sketching problem, like on your quiz, on your test, I'm going to have you fill these things out. It's the most important part of our function. The domain. What x values can we actually plug in? You need to know the domain so you know where your graph's going to be. Okay. If there are places where your domain isn't there, we need to be aware of any discontinuities. Okay? So are there any discontinuities? Are you going to have a hole? Are you going to have any asymptotes? Okay. Really, the biggest thing is going to be this right here. Who can tell me how we identify vertical asymptotes? Okay, if we have a function, whatever x values make our denominator 0 in the simplified version, we have vertical asymptotes. That is a very realistic possibility for some of these graphs. Okay? Next, I'm going to ask you to consider end behavior. Okay? We worked with end behavior with our limits towards infinity and negative infinity. Okay? With our limits towards infinity and negative infinity. And I'm actually going to put that on the quiz or test. Like, what's the limit towards infinity? What's the limit towards negative infinity? Okay? This could be a polynomial where we try to figure out the leading coefficient test. This could be a rational where we're trying to describe the horizontal asymptote. It could be a number of different things. Okay? Last pre-calc concept I'm going to ask you for are intercepts. Where are the x-intercepts? Where are the y-intercepts? Okay? Those are easy points to identify and place to help you get a shape. Okay, along with everything else. Okay. Now, let's get into the calculus stuff. Okay. What have I asked you to find? The first thing we talked about was increasing, decreasing, minimums, maximums. So I'm going to ask you to do that. Find our increasing and decreasing intervals. Find your minimums and maximums. What's going to be number 6? Concavity. Where do we have concave up, concave down intervals? Where do we have inflection points? Okay. Once we have all of this information, we can plot our intercepts. We can plot our minimums and maximums. We can plot our points of inflection. And then using our increasing, decreasing, concave up, concave down intervals, we can create a graph that matches the description that we have. You better believe it, I am going to look at your work, and it better match your graph. Okay? On a quiz, like if you do something iffy in your work, you're probably not going to have the correct graph. Do you see what I'm saying if you make a mistake? But your graph better match your work. Okay? Whatever your work says, that's the graph that you're going to put. Okay? So we're going to start off simple. I'm going to give you a polynomial because we know that those derivatives are nice to work with. I also know the algebra is nice too. Okay? What's the domain of any polynomial function? All real numbers. Does a polynomial have any discontinuities? No. They're always continuous terms. Okay? So we don't have to worry about any of our discontinuities. Okay? Our domain is all real numbers. Nothing crazy is happening. Okay? So let's talk about our end behavior. Okay? If we talk about going towards the right, so the limit towards infinity, the leading coefficient test would tell us that towards the right, what's happening with our polynomial? Is it going to rise or is it going to fall? It's going to rise. We have a leading coefficient that is positive. That right side is going to rise. Okay. Then we need to think about what's happening on the left side. If we go towards negative infinity, the leading coefficient test is going to tell us that the left side is rising or falling. Falling, we have an odd degree, and so our behavior is going to be opposite. Okay, so let's talk about our intercepts. Okay, y-intercept, we plug 0 in for x. X-intercept, we plug 0 in for y. Okay, so let's start with the easy one. If we plug 0 in for x, what's our y value? Okay, so 0, -1 is a coordinate on our graph. Now, I do want you to find x-intercepts. But for this equation, it's not a trinomial. We don't have a GCF. We really can't factor this, can we? Okay, so this is going to be an exception. I'm not going to make you figure out the x-intercepts because it's not pretty, right? We can't find it using factoring. I'm not going to make you go through any of, like, the synthetic division to try to, we're not going to do that, okay? We're just going to say, we're not going to find the x-intercept for this one, okay? I chose this one because, like, the derivatives are nice for us. But if I gave you a polynomial one, I'd either say, hey, don't find the x-intercepts, or they would be possible for you to find. Does that make sense? All right, so we're not going to worry about the x-intercepts on this one today. So let's start doing some calculus. Okay? If we want to figure out increasing and decreasing intervals, minimums and maximums, we need a derivative. We need a derivative. Okay? What's our derivative? Okay? So if we set that equal to 0, in order to be able to find those critical values, we can factor out a 3x. Left over is x minus 2. So our critical values are 0 and 2. So on our number line, we're going to throw a 0 and a 2 on here. Where are we plugging these numbers into? The derivative. We need to figure out, is our derivative positive or negative? So below 0, I don't know, -1. If we plug -1 into our derivative, what kind of values do we have? We plug a number in like 1 and into our derivative, what kind of value does it have? And then a number after 2, like 3. If we plug 3 into our derivative, what kind of value does it have? Now, on the quiz or test, I'll have a place for you to write the intervals of increasing and decreasing. Okay? This sign chart is a nice thing for you to look at. Okay. What's happening here at 0? We have a maximum. Okay, so let's make a note to ourselves that we have a maximum at 0 something. We have to plot this point. So we might as well figure out what it is. Okay, anytime I ask you for extrema, I want the actual coordinate. So at this point, we go to our original function. Oh, we already know that it's 0, -1, right? Our y-intercept is also our maximum. Okay. What's happening at 2? We have a minimum. We have a minimum at 2, comma. When we plug 2 into the original function, what do we get? -5? Okay, so there's another coordinate we'll be able to plot. And we know that it needs to change the directions there for a minimum. One more step. Our second derivative. If our first derivative was 3x squared minus 6x, then our second derivative is 6x minus 6. So when we set that equal to 0, we have x is 1. Okay. Could be an inflection point. Make sure you're labeling your sign charts, okay, because we're going to refer back to these here pretty soon. Okay, to the left of 1, is our second derivative going to be positive or negative? We plug 0 when we have -6, okay? To the right of 1, if we plug numbers into 6x minus 6, we would get positive numbers. Okay, so let's analyze this. If our second derivative is switching from negative to positive, what's happening at x equals 1? We have a point of inflection. I'm going to write POI, point of inflection, if that's okay. Okay. So our point of inflection is occurring at 1. We are going to have to plot that coordinate, so let's go ahead and find the y value. The original. Anytime we're talking about an actual coordinate, we need the original. Okay. All right. So question, have we done anything new? No, we've pieced a lot of things together, but nothing that has been a new concept. Okay? So now we're going to take this whole page of work that we just went through, and we're going to create a graph. All right? We have domain all real numbers, boring. We know the end behavior. Okay, we'll get there. Yes. So I will have a place for that for you to actually interpret the intervals. Does that make sense? Right now I'm not officially writing it just to kind of save some time. Yes. On a quiz, I'll have like all of this stuff for you to fill in, and that would be one of them. Yes. Concave up interval, concave down interval. Okay. So our y-intercept was it 0, -1? Okay. 0, -1 was also a maximum. Okay. What was our minimum point? 2, -5. Okay. And our point of inflection was at 1, -3. Okay. We also know, okay, our end behavior is rising to the right, falling to the left. Right? We'll eventually get there. But now we need to fill in the pieces. Okay? So look at your sign charts. We know that we are increasing until our max, right? and we're concave down to the right or to the left of 1. Do you agree? So we need to be increasing and concave down. We're going to switch directions at our max. Now our point of inflection means we change concavity. I see on our sign chart we have concave up after 1. So now I'm going to switch to concave up. Here we have a minimum, so I know we need to change directions, and we increase towards infinity. I don't know if you remember graphing polynomials in pre-calculus, but we would not have been able to graph this in pre-calculus. All we would have been able to find are the x and y intercepts. We didn't know how to figure out if it was turning somewhere besides the x-axis. Okay? So being able to do the calculus gives us way more accurate information as to what our graphs look like, which is nice. Okay. All right. That one was also nice because it was polynomial, right? Let's talk about the calculus side of things if it's not polynomial. Yes, it is. Okay. This will take us to the end of the period. Okay. This will take a lot of paper, like probably a full sheet of paper. Unless you write really, really small. Some of you are really good at that. What? Challenge accepted. All right, so first of all, the domain. Is our domain all real numbers? No, because we have moments where this is undefined. Where are those x values? Say it louder, Yovna. -2 and 2. So our domain is everything except -2 and +2. Why are we excluding 2 and -2? Yes. Yes. And graphically, we have vertical asymptotes. You said all the right things. But I want to talk about what's happening on the graph. On the graph, we have asymptotes. Okay, there are our points of discontinuity. Now, is a rational graph subject to only vertical asymptotes? No, there could be a horizontal asymptote, and we're going to figure that out by looking at the end behavior. Turn to your neighbor and talk about where you think the horizontal asymptote is. I don't hear a lot of talking for a turn to the neighbor instruction. Okay. Yes, our asymptote is at y equals 2. Because the degree on the numerator and denominator are the same. Remember those rules? Numerator and denominator have the same degree, so we look at the coefficients. If the denominator was bigger in degree, then we'll get 0. If the numerator was bigger, there would not be one. We would have a slant asymptote. I will not give you one of those. Okay. What's our fourth step? Intercepts? Yep. And behavior was that horizontal asymptote. Okay. All right, so our intercepts. Let's start with the easy one first. When we plug 0 in for x, leftover is? Uh-huh. Okay. Now, if we're going to set this equal to 0, it's really just the numerator. Do you agree? Okay, so we're talking about 2x squared minus 18 equaling 0, which is essentially asking for where is x squared equal to 9. So we have 2x intercepts, one at negative 3, 0, and one at positive 3, 0. Yes? Well, I set the whole thing equal to 0, but then if we were to try to solve that, we would take our denominator and multiply it over. And 0 times the denominator would still be 0, so it ends up with just the numerator. So shortcut, if you wanted to set the numerator equal to 0, you're finding your intercept. Okay? All right, you ready? All right. Yes. I plugged 0 in for x, and so we had negative 18 over negative 4, and we simplified to this. What are we going to have to use to find our derivative? Quotient rule. Okay, you ready? All right, derivative of our numerator is 4x times our denominator, x squared minus 4, minus our numerator, 2x squared minus 18, times derivative of our denominator, 2x, all over denominator squared. What are we going to have to do with that? We're going to have to simplify it. Okay, so we have 4x cubed minus 16x minus 4x cubed plus 36x. Why is it positive? Okay, we have to distribute that 2x through, but then also this is subtracting all of it. So that subtraction gets distributed as well. But there's not an x squared minus 4 over here. No, because like if that were 2x squared minus 8, we could, because that would be like an even multiple. But since these aren't the same, we can't do that. But in our second derivative, we will be able to. Okay, they need to be like the exact same. Okay. So what's in our numerator? Did you say something so that I didn't notice? Come here. Okay, so when we make a number line here, okay, 0 makes our derivative 0. Negative 2 and positive 2 make our derivative undefined. Well, what's happening at -2 and +2? What did we decide early on? What's happening there? We have asymptotes. So I'm going to make a note to myself that these are asymptotes because we can't identify them as minimums or maximums, but we do need to know where we're increasing and decreasing, so they're still important. They're still critical. Just to save a little bit of time, I'll do this for you. Okay? Because I want to make sure we spend some time on that second derivative, because it's pretty gross. Okay? So what do we have? We have a minimum. And our minimum occurs at 0. We already know that the y value is 9/2. So far, so good. Now, at this point, you need to make a decision about which form of the derivative you're going to use to take your second derivative. You're talking about a quotient. Okay, let's go to the most simplified version. If you had two terms that you forced to have equal denominators to combine, you could go back to those two separate terms if you wanted to. Okay, but let's go from here. So for our next quotient rule, we have the derivative of the numerator times the denominator minus our numerator times the derivative of our denominator, 2x squared minus 4 to the first power times chain rule 2x, all over our derivative squared. Now, Jesse, this is what you were trying to look at, right? When you do the second derivative of a quotient rule, you need to look for this, okay? In the numerator, do you see something in common? I see an x squared minus 4 to the first power. Anything else in common? I see 20. And whether you get 20 out or not, that's really not going to make a big difference. But you got to get this x squared minus 4 out. So left over here would be one of the x squared minus 4s. Minus here, we took the 20 out. We have x times 2 times 2x. So we took the 20 x squared minus 4 out. Here, we had 1 left over. Here, we took the 20 out. We took the x squared minus 4 out, so we had x, 2, and 2x.
I was thinking whether we could do like 2 sets and
Okay, whoops. So why was that nice? This guy cancels out with one of these. And we're left with 20 times negative 3x squared minus 1 all over x squared. You don't have to. You can leave it like this, or you can have negative 60x squared minus 80. I don't really care. But what happens when you try to set this equal to 0? Is that okay? Okay, so it doesn't equal 0. That's okay. That happens sometimes. Okay? So the only thing we need to worry about on our number line is where the denominator is 0. And remember, -2 and +2 make our denominator 0 because originally they were asymptotes. So even though our sign chart goes negative, positive, negative, those are not inflection points because they're asymptotes. So we actually don't have any points of inflection because where we change concavity are actually asymptotes. There aren't any points there. Now we get to graph this, right? Okay, so first of all, are there any questions about the algebra or calculus before we graph it? Yep. So we'd be concave down from -infinity to -2 and 2 to infinity. We'd be concave up from -2 to +2. Yep, and you'd identify those intervals for me. Okay. But right now, let's just look at our charts and go ahead and graph it, okay? What's the first thing we should probably plot? Our asymptotes are pretty important. Okay. Then we have intercepts at 3, 0, and -3, 0. And we have an intercept of 0, 9 halves. 2, 4, 6. There we go. Okay, you ready? Piece it all together. To the left of 2, we are negative, derivative, negative, second derivative. Decreasing and concave down, and we know it should approach the asymptotes. To the right of 2, positive derivative, positive, negative, second derivative. So we are increasing, concave down, and then here we're concave up, decreasing, then increasing. Ta-da! Yes. This was our horizontal asymptote. The y equals 2, like our end behavior. When we talked about end behavior, the limit towards infinity and negative infinity. And before you ask, yes, this would be something I would ask on a quiz or test. Yes. Now, how many questions are you going to have?
Like
1. So 0, 9 halves we identified as a minimum. And then we know it's concave up because our second derivative is positive. And then we have increasing or decreasing, increasing. Yeah?
Although tomorrow I'm going to do my thing. Okay, so there's that. So
I'm recording, so hold on.
Mrs. Holman is a great calculus teacher, and I'd like just to say that, I have a lot to learn from her.